If you want to do very small signal electrical measurements, there's usually external noise present that has nothing to do with the actual signal. This noise can be hundreds of times more than the expected noise of the system. Usually, you want to measure the voltage at a certain point with respect to common or ground. Unfortunately, that common or ground is often noisy compared to the ground of the oscilloscope or amplifier or voltmeter that you're using. This is because of ground loops and direct capacitive pickup of external fields. This noise can be eliminated by using a precise differential amplifier, which contains two separate amplifiers to measure the difference between the signal and its ground. Each input of the differential amplifier has high impedance, and the two amplified signals are precisely subtracted from each other, meaning that their gains have to be identical. Here's an example of a small signal being directly measured by an oscilloscope versus using a differential amplifier and then sending that signal to the oscilloscope. This oscilloscope is set to its maximum vertical gain of 2 millivolts per division. The bandwidth limit is also on. There's a little bit of noise now, but more noise when a cable is connected. Here's a signal generator with a 1 kilohertz square wave that's 10 volts peak to peak. It's connected to a very simple circuit, a voltage divider. The input goes through a 10,000 ohm resistor, then through a 10 ohm resistor to ground. At this point, the output is divided by a factor of 1,000. When I connect the oscilloscope across this, it will be 10 millivolts peak to peak. There's a significant amount of noise, around half a millivolt, and this is far more noise than what it should be. Now I'll use a differential amplifier to look at the difference in voltage between this point and this point, connecting this point to the positive input and this to the negative input. It will subtract the two from each other, then multiply by a gain of 10, which is the minimum gain of this amplifier, so I'll adjust the oscilloscope to make the trace fit. This differential amplifier is set to a low-pass filter of 400 kilohertz, the same as the oscilloscope. There's a much better signal-to-noise ratio now. If you're curious, this is the positive input by itself, and this is the negative input. Once they're subtracted from each other, you get a very clean signal. In fact, the signal can be reduced by a factor of 10, so that we have 1 volt peak to peak coming out, and it's divided down to 1 millivolt peak to peak. I'll increase the amplifier gain by a factor of 10, so now it's 100x gain. It's still a much cleaner signal than when the oscilloscope was directly looking at a 10 millivolt square wave. Here's what the positive input is seeing now, and the negative input, but they subtract to make a clean signal. This can be reduced by another factor of 10 to bring the signal down to 100 microvolts peak to peak. Now the signal-to-noise ratio looks about the same as when the oscilloscope was directly reading the 10 millivolt square wave. This means that the noise has effectively been reduced by a factor of 100 simply by using a low-noise differential amplifier. The signal can be reduced by another factor of 10 to make it a 10 microvolt peak-to-peak square wave, and I'll take the bandwidth down to 10 kilohertz to reduce the thermal noise. This is set to DC coupling, but you can also couple by AC if the inputs have a big DC voltage difference. These digital scopes do have something like a differential amplifier. The math function can be used to display channel 1 minus channel 2. Both channels here are a 1 volt square wave. I can use the math function in several ways. The channels can be added to make a 2 volt square wave, or they can be subtracted like this. That's the differential. It's a bit noisy at 1 volt, but how well will it work for smaller signals? Here is channel 1 minus channel 2. Both channels are set at 2 millivolts per division and still at 400 kilohertz bandwidth. The input is a 10 millivolt square wave. Stopping the waveform, the whitish blue is the differential, channel 1 minus channel 2. Spreading it out in the horizontal, it's obviously quite noisy. This is because the two oscilloscope inputs are digitized first and then subtracted, but there's only 256 levels of digitization. You'll need more like 1,000,000 levels for reasonable noise cancellation. Of course, an analog amplifier can achieve that level of precision. Also, these two amplifiers need to have the same gain with very tight tolerance, which is not the case with an oscilloscope. The two gains in this amplifier, however, are matched to within 1 part in 100,000.